So we're mixing together 1.2 kilograms of liquid water at 10 degrees and 0.5 kilograms of solid water initially at negative 20 degrees. If we want to figure out what's going to happen here, first of all, which direction would we expect heat to flow? What's going to be gaining energy versus losing energy here?
From water to ice.
Yeah, we expect the liquid water to lose energy because it's the higher temperature, and the solid water to gain energy because it's exactly, from the warmer to the cooler object. Heat typically flows from the high temperature zone to the low temperature zone. So we expect the liquid water to be losing energy and the solid water to be gaining energy. But we need to figure out what type. And at the very beginning, it looks like these are nowhere near their phase change points yet. So what type of energy is going to be changing? Yeah, we're going to have a change in thermal energy. So the liquid water is going to be losing thermal energy. And since these are both water, it gets kind of confusing to say which is which. So I'm going to label these, let's say we call the liquid object A, and we call the solid object B. And that way we can still call them object A and object B even if they change phase. Like maybe the liquid water starts to freeze. It gets kind of confusing to refer to the original ice versus the new ice that has formed. But if we can still call it object A and object B, that makes it easier to refer to. So thermal energy of object A is decreasing, corresponding to a temperature decrease. We even know its initial temperature is 10 degrees Celsius. Final, we don't know. Also, the solid water, object B, is gaining thermal energy, corresponding to an increase in temperature. We know it starts at negative 20 degrees Celsius, and we don't know how hot it gets. And the thing is, there are several options here, several possibilities. Because we don't really know exactly where in the middle they meet. We don't even know how much it's going to change phase or which one is going to change phase, if either. But what we can do to find out, I find it often useful to look at extreme cases. Like we have, let's say, a moderate amount of ice and a moderate amount of liquid. But suppose they were extremely different. Suppose we had lots of liquid water at 10 degrees, and we had just one tiny ice flake. At negative 20 degrees, and we drop those into each other. In that case, if you have a tiny amount of ice and lots of liquid, what would you expect to happen? Yeah, presumably all this ice, and of course it can't melt yet because it's at negative 20, but it will melt once it reaches what? Yeah, once it reaches 0. And if this is a very small amount of ice and lots of warm water, well, warm-ish, then presumably the ice is going to warm up to 0 very quickly and melt very easily, while the liquid water hardly changes at all. So the result, in this case, would be ice warms up, melts, and warms up more, reaching almost 10 degrees. Meanwhile, liquid water, object A, cools down a very tiny amount. Liquid cools a little bit. So T final would be maybe 9.9 degrees, just as a guess. And presumably all liquid. So this is one possible result. if we had lots of liquid water and only a tiny bit of cold ice. Or if we take a look at another extreme, suppose instead we had a huge amount of ice, but only a little bit of liquid water. Suppose we had this giant block of ice at -20, and we had just one single drop of liquid water at 10 degrees. In that case, what would you expect to happen when this tiny drop hits the giant block of cold ice? Yeah, it's going to freeze. And of course, it can't freeze yet because it's 10 degrees, but it would rapidly cool off to 0 and freeze, and presumably keep cooling off almost all the way down to -20. Meanwhile, the ice is going to warm up very slightly to maybe -19.9 or something. And so the whole system would be solid at -19.9 degrees or something like that. So that's another possibility. Another possible result, if we have lots of ice and only a little bit of warm water, is that everything freezes. The drop freezes. Everything is at T final equals, let's say, about -19.5 degrees, and all solid. So those are the extremes. These are basically the most it can go in either direction. The hottest everything can get is almost 10 degrees and all liquid. The coldest everything could get is almost down to -20 degrees and all solid. But since we don't really have a huge amount of liquid or a huge amount of solid, we've got more of a moderate amount of both. I would expect the final result to be actually somewhere between these. But we've at least established the extreme possibilities. The extremely high-end possibility, 10 degrees and all liquid. Extremely low-end possibility, -20 degrees and all solid. Realistically, somewhere between those. But the problem is we don't know in advance which one it is, which means we can't really complete the conservation of energy or the energy interaction diagram. Because in one extreme, the liquid water changes phase, but the solid water doesn't. In the other extreme, the solid water melts, but the liquid water didn't change phase. So we don't really know whether we should include bond energy of the solid increasing as it melts, or bond energy of the liquid decreasing as it freezes. And we can't tell that just from the diagram so far. We're going to need to make some other calculations to figure that out. Any questions on that so far? So let's try this. We know that the liquid water is going to be cooling down. We know the solid water is going to be warming up. Any thoughts on how we could tell which one of those is going to start their next phase change? What is the question asking? Ultimately, we're just trying to figure out if we wait long enough, what's the final temperature going to be and how much in each phase, how much solid, how much liquid. So we want to know if we wait for everything to settle down to equilibrium, that is everything at the same temperature, what does the final result look like? So to figure that out, we're going to need to be able to tell which one of them goes through a delta E bond, a delta phase change. MC delta T will help us figure out the delta E thermals. How could we use that to figure out which one goes through a phase change? Like, how would we figure out if we're more like this, where the drop of the liquid water starts freezing, or more like this, where the solid ice starts melting? How could we tell which one of these hits a phase change first? Yeah, we can compare the amount of energy. Because in order to get to a phase change, this one would have to cool down from 10 degrees down to 0 degrees. This one would have to warm up from -20 degrees up to 0 degrees. Whichever one gets to its phase change point first is going to start going through a phase change before the other one does. So let's try that. Let's check both of those possibilities. We're going to have to set up some hypotheticals, some what ifs, some maybes. We could say maybe the liquid water cools down to 0 first. Or maybe the solid water warms up to 0 first. So let's set both of those up. Maybe object A cools to 0 degrees first. Or maybe object B warms up to 0 first. So we want to check both of those maybes and see which one actually finishes first. And to do that, we can take a look at how much energy it takes. For instance, A cooling down to 0, that's a delta E thermal. And yeah, we could use that usual formula, mass times specific heat times change in temperature. We know the mass of A is 1.2. And where could we get specific heat? How would we know the specific heat for this situation? Yeah, and where do we get that? Yeah, we can just look that up on a data table. Look up specific heat of liquid water on a data table. And yeah, we want to check which one requires less energy. Yeah, solid is a different value. We've got solid and liquid, yeah, 4.18 versus 2.05. 4.18, and we specifically want to use the one with the right units, kilojoules per kilogram Kelvin. Whereas for the solid, we're still using the same formula, but the mass is 0.5 kilograms. And the specific heat is, I think it's 2.05. Yeah, 2.05 kilojoules per kilogram Kelvin. And of course, they're going through different hypothetical temperature changes also. For the liquid water, object A, we're assuming it cools from 10 degrees to maybe 0 degrees. What's the delta temperature for that? If we're starting at 10 degrees and we're assuming we end at 0 degrees, yeah. Yeah, we would use -10 here because we would be using final minus initial. 0 degrees minus 10 degrees is -10. And because it's a change, Kelvin and Celsius are interchangeable. Losing 10 degrees Celsius is exactly the same as losing 10 kelvins. So I'm just going to write this as -10 kelvins to make the units work out nicely. Kelvins and kelvins cancels out. Kilograms and kilograms cancels out. We're left with kilojoules. So 12 times 4.18 is going to be 50-ish. -50.16. -50.16. So that means in order for object A to cool off to 0 degrees, it has to lose 50.16 kilojoules of energy. Meanwhile, for the solid water, object B, we're assuming it warms up from -20 up to 0. So what would be delta T for that one? Yeah, it would be gaining 20 degrees Celsius or 20 kelvins, so plus 20 kelvins. Once again, the units work out nicely. Kelvins and kelvins cancel out, kilograms and kilograms, because we chose the value that had the units of measurement that already match up. So 1/2 times, so that's just going to be 10 times 2.05, so 20.5. So delta E thermal would be positive 20.5 kilojoules. So that's how much energy the ice would have to gain in order to warm up to 0. Whereas this is how much energy the liquid water, object A, would have to lose to cool down to 0. So based on this information, which one finishes the process first? Yeah, object B cools down or warms up to 0 first because it takes a smaller amount of energy. It is easier to warm up B to 0 than it is to cool down A to 0. And remember, these are interchanging energy at equal rates. If object B gains 1 joule of energy, object A loses 1 joule. Gain 1 joule, lose 1 joule. Gain 1 joule, lose 1 joule. So in the time that it takes this one to gain 20.5 kilojoules, which brings it to 0, this one has lost 20.5 kilojoules, which is not enough to bring it to 0. So this one finishes first. You just need to compare the magnitudes, the absolute values of those temperature changes to figure out which one reaches its phase change point first. That means that the ice has warmed up to 0, its melting point, while the water is still warmer. The water is still maybe at 5 degrees or something, which means if you now have ice at 0 and water that's still warmer at 0, what's going to happen? What's our next step going to be? We do want to find the final temperature, but just conceptually, what's going on here? If you've got ice at 0, yeah, the ice is going to go through a phase change. That doesn't necessarily mean it's going to all be liquid, but it's at least going to start melting. So that's our next big question. Does it all melt or does it only partly melt? Right, we need to figure out how much energy will it require to melt all of it, and is that actually going to happen? So that's our next big maybe. We know that, yes, the ice does warm up to 0 degrees. We know the liquid water hasn't cooled down to 0 degrees yet. Our next big question is, what happens next? Does the liquid water cool all the way to 0 while the ice is still in the process of melting, or does the ice all melt before the water cools off to 0? So let's check that as our next big question also. Maybe B all melts. And we'd also need a maybe A cools off to 0, but we've already got that. We know it takes A this much energy to cool off all the way to 0. So let's check how much energy it would take for B to all melt. What type of energy change would that be? Yeah, that would be delta E bond. And what formula could we use for that? Yeah, delta M, delta H. Delta M is how much of the mass changes phase, and delta H is just a constant we can look up, the heat of melting. What would be delta M? If we're assuming it all melts, what's the value of delta M here? Yeah, the full 0.5 kilograms. Because if you look at just object B starts with no liquid and ends with ½ kilogram of liquid. Final minus initial would be 1/2 kilogram minus 0 kilograms. So we'd have 0.5 kilograms, positive 0.5, because we're gaining liquid, gaining the higher energy state. And then delta H we can look up on a data table. So delta H for water, heat of melting, 333.5. And that's kilojoules per kilogram. So 1/2 of 333.5 should tell us the amount of energy it takes. That's 150, 165, 166 and a half, 166.75, I think. And positive, of course, because we are adding energy. So this is how much energy it would take to melt the whole thing. The one that finishes first, yeah, because that would be the one that goes through the next stage of the process. We know that the object B reached its phase change point first, while object A was still in the process of cooling off. So object A is just going to continue cooling off because it hasn't reached 0 yet. But meanwhile, object B is gaining more energy, which means it starts to melt. Because this energy that A is able to provide is enough to completely warm up B all the way to 0 and start melting it. Is it enough energy to finish melting it? Does the energy that A can provide, is that enough energy to completely melt the ice? No, it's nowhere near enough, right? Because we can, as A cools down to 0 degrees, which is the coldest it can get, really, A can afford to lose 50 kilojoules. 50 kilojoules is more than enough to warm up the ice to 0, because that only costs 20 kilojoules, 20 and a half. But to warm up the ice to 0 and completely melt it would take 20 and a half plus an extra 166.75. So that's about 190 kilojoules. That's way more than the amount of energy available. So as A cools off, it's going to warm up B to 0 and partially melt, but definitely not completely melt, nowhere close. So that suggests we're going to end up with some liquid and some solid still in the system. And if we end up with some liquid and some solid, what temperature does that have to be at? Yeah, it's got to be at 0. So we know the final temperature of the whole system is going to be exactly 0 because we end up still in a mixed phase. So we can fill in more of this energy diagram. We know that the final temperature of both of these is going to be 0. We can now fill that in for sure. We know they will both reach 0 eventually. We know that the ice partly melts, but not completely. So the 166.75 is the amount of energy it would take to melt all the ice, but we know that's not going to happen because the liquid water, as it cools off, cannot provide that much energy. It doesn't have enough available energy to provide. So we are going to have a delta E bond for the ice, for object B, but it's not going to be at the complete 166 and 3/4 kilojoules. Instead, it's going to be a partial delta E bond. So the bond energy for object B is going to be increasing as it melts, as it partly melts, because the mass of liquid is going to go up. But the problem is we don't know how much it's going to go up. So let's label some M initials and M finals. How much liquid do we start with? Yeah, we could say we start with the 1.2 kilograms of liquid here. And there's actually a couple of ways you could go about this. You could say we start with 1.2 kilograms and we're going to end with more than 1.2 kilograms of liquid because we gain liquid. Or we could look at just object B and say object B starts off with no liquid and ends up with more than 0 liquid. So we could go either way. It might be useful to just call this some unknown delta M here for now. Delta M equals question mark. Instead of splitting out delta M into M initial minus, or M final minus M initial, we could just treat delta M as our unknown and solve for delta M. And I think that's all the types of energy that are changing here, because we've got the object A, the liquid water, getting colder all the way to 0 over a long period of time. Object B, the solid ice, getting warmer, warming up to 0 much faster. And meanwhile, and then after that, the ice starts to melt. That's all the types of energy that are changing. Would you expect this to be called a closed system or an open system here? What do you think would make more sense? And when would we call that open?
Do we not consider that B might start to, A might start to freeze in this process?
Well, the thing is, in order for liquid to freeze, it has to cool down to its freezing point and then lose more energy. In this case, A is cooling off to its freezing point, 0 degrees. But the thing is, object B got to 0 first. As soon as A gets to 0, what do you know about all the temperatures in the system?
Oh, is it because B has less total energy than A or something like that?
Not about total energy, because we don't really care how much energy there is. What we care about is how much energy changes. But the important thing is, in order for heat to flow, what causes heat to flow in the first place?
One has more energy than the other.
It's not about more energy. It's about, a temperature difference. Heat goes from high temperature zone to low temperature zone. So the only reason heat is flowing in the first place is these are at different temperatures.
So a difference in
0. Yeah.
Okay, so a difference in bond energy isn't like if they're the same temperature, but one is a little more frozen than the other, it still wouldn't cause heat to flow. Is that what you're saying?
Yeah. Yeah. Well, if they're at different temperatures. The heat flows only if there's a difference in temperature between the objects. But as soon as they reach the same temperature, if you've got solid ice at 0 and liquid water at 0, those are now at the same temperature, so there's no more heat flow, no more interchange of energy.
That makes sense.
So, and that's what we call thermal equilibrium. Thermal equilibrium just means everything has reached the same temperature, which means there's no further flow. And yeah, I think we would call this closed because we've got energy transfer. There is heat flow, there is energy transfer, but all the heat flow is between objects that we're considering to be part of the system. There's no energy entering or leaving from elsewhere. Presumably, we're mixing these together in an insulated container or something like that. So I would treat this as a closed system because we're only considering energy exchanges between objects that are part of the system. And that means, what does that tell us about all three of these delta energies? What would those have to add up to? Yeah, we can say those delta energies add up to 0. So let's try writing that up. We can say delta E total equals 0. And then we can fill in the individual types of energy. We've got thermal energy for object A. We've got a change in thermal energy for object B, the solid ice. And we've also got a change in bond energy for object B as it partly melts. And we know those changes have to add up to 0 because it's a closed system, no heat or work entering or leaving. And usually we would then fill these in with MC delta T and delta M delta H. But the thing is, we already did these calculations. We know object A is cooling down from 10 degrees to 0 degrees. How much energy does it take for object A to cool from 10 degrees to 0 degrees? Yeah, that's the negative 50.16 kilojoules that we already calculated. So we don't need to calculate it again. We know that, because this was a maybe, what if object A cools down to 0? We know that it really does cool down to 0. So we can use this value, negative 50.16 kilojoules. And what about object B warming up to 0 degrees? Yeah, the plus 20.5 kilojoules, we can use that as well. And I erased it, but can we use the 166.75 kilojoules for delta E bond for object B? Yeah, we can't use that one, right? Because the 166 kilojoules, that was the amount of energy involved in what change? 166 was the amount of energy required to do what? Right, to melt all the ice. And we know the ice doesn't all melt. There's not enough energy left over in order to melt all the ice. Nowhere near enough. So there's only enough energy to melt some of the ice. The 166.75 kilojoules was melting all of the ice. We know that doesn't happen, so we can't actually use that number. Instead, we would use a delta M, delta H. Of course, we can still use the delta H we looked up, the 333.5 kilojoules per kilogram. And we know those have to add up to 0. But now this equation only has one unknown left. Delta M is the only unknown left. So we can solve that algebraically for delta M, and that will tell us how much material changes phase, specifically how much of the ice melts. Any questions on that setup so far?
Can you go over again why you would use the 333.5 value again?
Yeah, that is specifically, if we set up the delta E bond as our usual delta M times delta H, delta M represents how much of the ice melts, and we don't know that yet. That's going to be an unknown, so we just leave it as an unknown delta M. But delta H is a property of the material. Delta H basically represents how difficult it is to melt. More specifically, how much energy it costs to melt exactly 1 kilogram. And that you can look up on a data table. So you look that up on, what is it? Right here, if you can see that all right. 333.5 kilojoules per kilogram. That's the amount of energy per kilogram it takes to melt ice. So we've got an unknown amount of mass times 333.5 kilojoules per kilogram of that mass. Any other questions on that so far? And then it looks like the rest should be algebra. We can combine like terms, move anything without the variable to the other side, and divide by a coefficient, and that should give us the value of delta M. So, and what steps would you take here? How would you actually find delta M here? what would be your next algebra steps? Yeah, these numbers we can just add together. That gives us negative 30, negative 29 something. Be a little more precise than that. Negative 29.66. So pretty close to negative 30. Plus this unknown delta M times 333.5 equals 0. And then what? Yeah, we can do that by adding 29.66 to both sides. And we get delta M, which is unknown, times this coefficient, 333.5 kilojoules per kilogram, equals 29.66 kilojoules. And then what? Yeah, then we can divide by 333.5. And I would keep the units attached to that. We're not just dividing by 333.5. We're dividing by 333.5 kilojoules per kilogram. That way, when we divide the units, and yeah, that'll be 0.089. And as for the units, kilojoules and kilojoules cancel out. And then we've got 1 divided by kilograms. That flips the fraction and makes it kilograms. So we end up with delta M equals 0.089 kilograms. In other words, that's how much ice turns into water. So if we want to know the final amounts of both substances, we started with 1.2 kilograms of liquid. We gained 0.089 kilograms more liquid. So we'd have 1.289 kilograms of liquid. We started with 0.5 kilograms of solid. We would remove this amount of solid. So 0.5 minus 0.089 tells us how much solid is left. And then that will all be at 0 degrees. Any other questions on that so far? You're welcome. Any other general questions or anything else you want to work on?
For the the change in bond energy, in the lectures, they also put that the equation could also be the absolute value of delta M, delta H. And I was wondering when those absolute values would apply.
I generally wouldn't. They often teach it as plus or minus absolute value, the idea being that you strip off any positive or negative signs and then choose a positive or negative sign manually. But the thing is, as long as your indicator, as long as you're always using mass of the higher energy state, the correct plus or minus will automatically show up. Like in this case, for instance, if you take a look at the final amount of liquid, which is a higher energy state, minus the initial amount of liquid, we started with 1.2 kilograms of liquid. We end with more than that. A larger value of liquid minus a smaller amount of liquid is going to be a positive number corresponding to the increase in bond energy. If you're going the other direction though, like let's say you take some liquid and you freeze it, you end with less liquid than you started with. So final small amount of liquid minus initial large amount of liquid would be a negative. So that negative automatically shows up in your delta M when you subtract final minus initial. So as long as you're careful to always use mass of the higher energy state, in the sense that gas is higher than liquid and liquid is higher than solid. If you always use mass of the higher energy state as your indicator, then the correct positive or negative sign will automatically show up when you subtract final minus initial.
Oh, okay, that makes sense. Thank you.
Mm-hmm. And I would still recommend thinking through in advance, like just ask yourself, should I expect this to be positive or negative? And then check to make sure it really is when you do the calculation. So make sure you, but that's not just for bond energy, that's for really any type of energy. whether it's thermal energy, bond energy, the kinetic and potential energies that we're going to see later, before you even run the numbers, ask yourself, should I expect this to be an increasing or decreasing value? Should I expect the delta to be positive or negative? And then keep that in mind as you're running through the numbers so you can compare at every single step. Does this look like what I expect it to? And if it doesn't look like what you expect it to, then maybe something's gone wrong with the calculations, or maybe this is a really weird counterintuitive situation. That happens sometimes also. Physics doesn't always do what we expect it to because it's not always describing situations that we have a lot of intuitive experience with. So don't necessarily trust your intuition all the time, but also don't ignore it. Physics is talking about everyday physical situations, and you have years of experience with that. So think about, and in all of these cases, ask yourself, what would I expect to happen here without even doing any calculations? Then run the calculations and see how closely it matches up. Any other questions on that? Or any other questions on the conservation of energy stuff in general?
Just a quick question about the problem we just did. So, there's like an energy exchange between A and B. So when the fact that it only takes 20.5 kilojoules for it to melt means that the rest of the energy that it's like, I don't understand like why it's phase changing.
It takes 20.5 kilojoules to warm the ice up from -20 to 0, but no phase change has happened yet.
Yes.
So 20.5 kilojoules to go from -20 to 0, then any more energy you add beyond that goes into melting some of the ice.
Oh, and then the energy that's considered like the excess comes from the energy that's lost from the liquid?
Exactly. As the liquid cools down to 0, it's able to lose 50 kilojoules. The first 20.5 kilojoules go into warming up the ice. The other 29.66 kilojoules left over go into melting some of the ice.
I see. Okay, thank you.
And of course, that's, again, nowhere near as much as the 166 we would need to melt all of it. So we don't melt anywhere near all of it.
Okay, thank you.
In fact, this 30-ish kilojoules is about a fifth of what it would take to melt all of it. 30 is about it's a fifth of 150, so a little less than a fifth of 166. Since the energy available, the extra 29.66, is a little less than a fifth of what it would take to melt the whole thing, that means we end up melting a little less than a fifth of the total amount of ice. 1/5 of the ice would be 0.1 kilograms. We melt a little bit less than that, 0.1 kilograms.
Okay.
So it's proportional.
Mm.
Any other questions on that?
Oh, sorry, just like one last question. How would you know if it would end in a mixed phase versus like an absolute phase? Like, for example, like if it melts to all like liquid or vapor?
In this case, it's because the liquid water cooled off to 0 before the ice finished its phase change. If we had like, let's say the liquid water had started off way hotter, maybe at like 90 degrees or something. In that case, maybe the liquid water cools off and the ice warms up. The liquid water keeps cooling off, the ice completely melts. And then after that, the liquid water would keep cooling off and the new liquid water would warm up. And they'd meet somewhere above 0, all in the liquid phase. So in that case, you need to check several more of the maybe situations. Maybe the liquid water cools off all the way to 0, or maybe the ice completely melts. And then see what happens next. Keep doing those maybes until they actually meet somewhere in the middle.
Oh, okay. So it's like a lot of like trial and error type of.
Yeah. And then once you find how they actually meet, then you can set up the complete energy interaction diagram, turn it into an equation, and solve for that last unknown. And typically the last unknown will be either what temperature do they meet at, or if they end in a mixed phase, what fraction is liquid versus solid or whatever. And you can get some more practice on that with the worksheet I linked. If you go to math.ncheese.org/P7A, there should be a worksheet with a whole bunch of practice problems on stuff like this, where there's several steps you need to consider. And that also has answer sheet at the bottom and lists out all of the important specific heats and delta H's you're going to need. Worksheets for future topics. I don't have any worksheets for future topics yet, other than a practice final that covers a little bit of everything. But I'd like to add more to that. So if there are, as we go forward, if there are other topics you'd like more practice on, let me know and I'll try to write some worksheets for those as well. All right, that's about it for today, but feel free to contact me online if you want to request any topics for next time, and I will see you then. You're welcome.